Hello and welcome to Networking Part 3. In this episode I'm intending to just tie up some of the loose ends that we've left behind from parts 1 and 2. Also, because of some in real life scheduling difficulties, this video is going to be a little bit shorter than normal. This was explained a few weeks ago in my little update video. So far in this series we've developed a very simple to use framework that's also quite flexible, but it does have some limitations. And I feel that we'll definitely need to address these before we can start implementing a game, or before you can start using it practically in your applications. By the end of this part, I hope that the networking library that we've developed will be sufficient for most casual or hobby programming projects. At the end of the previous episode, we'd created a server and a client program, and we could have multiple client programs talking to the single server. And in fact, the clients could also talk to each other. Up here in the top left we see the server and we can see 3 connections have been made. And if I press the 1 key in one window it pinged the server, and we can do that from the individual clients. We can also get one client to send messages to the others. But if you can feel your room heating up, it's worth bringing in Task Manager and having a look why. Here are my 3 client applications and my server application, and we can see that the client applications are occupying a full processing core each, and in fact so is the server. In reality, I'll probably want to host our server application on some virtual private server, which will be part of a shared cluster somewhere else in the world. If I chose to host it on the onelonecoder.com web server, well, that server's also got to serve my website and other various things the community use. It's no good if my server application is consuming all of the processing resources available to the server. Well, not always anyway. At the moment, our entire networking infrastructure is simply just pinging messages to and from each other, and we're doing it asynchronously to try and do away with utilizing the CPU at 100% load waiting for information. Whether you want your server application to do this or not is application dependent. In this simple example, it makes no sense for the server to sit here consuming lots of resources. But let's suppose that our server had some server-side game logic to facilitate. Then we probably do want it sat there doing the game logic and occasionally responding to messages. Perhaps the in-game world has some artificially intelligent bots or something running around it. What's going to be responsible for updating those? Well, it's the server, and it'll need to do that in between processing all of the requests from clients. In that situation, it's probably more likely I would want my server application to utilize a full core of the CPU. And if I was rolling it out and taking it very seriously, I would probably hire a dedicated serving framework that will just sit there running at full throttle all the time. However, for now, I do want to share the server's load with other things that the server wants to do. The client applications also occupy a full processing core. I'm less concerned about these. That's because at the moment our simple demonstration application just has a tight while loop, where it continuously checks for keyboard input and continuously checks to see if messages have been received or not. Also, particularly with regard to games, it's quite likely that I do want my client application utilizing a full CPU core. If it's not responding to networking, I want it processing game logic, I want it updating graphics, I want it doing all the things I'd expect a client to do. But certainly for our server, I believe this is a problem. Our server program is very simple. There's int main, and we simply repeatedly call server update in a very tight infinite while loop. In this example case, our server has nothing to do most of the time. In fact, it only ever has something to do when a client sends something to it. So it would be far better to get the server to sleep until a message has been sent to it. We can implement this in the update function. As I've just discussed, whether I want the server fully running all the time or not is, well, it's application dependent. So I'm going to specify a Boolean flag here that allows me to enable waiting or not for a client to communicate with the server. And by default, I'll set this to false. Because we've taken the time to design an architecture where all incoming messages are ultimately funneled down to one input source for this entire server, all I need to do is sleep until that input queue contains a message. Therefore, in the condition that I want to wait, I'm going to create a wait function on my thread-safe queue. The wait function will be blocking, and when it is called, it will suspend the calling object until a message is written to the queue. To implement this signaling, I'm going to use a condition variable. Now, we have used these 1 or 2 times before, And to protect my condition variable, I'm also going to create a mutex called mux blocking. The wait function primarily contains a very tight loop that checks whether the queue is empty or not. If it is empty, then this empty function returns true, meaning the calling process is locked inside this while loop until it returns false, and the only incident of it ever returning false is when something else is written to the queue by some other thread. However, all this has done has moved our tight while loop from one place to here. It will still occupy 100% of a CPU core while sitting in this while loop. Therefore, inside this while loop, I'm going to use my condition variable to send the thread to sleep, and it will wait here until something signals the condition variable to wake up. Two things can signal a condition variable to wake up. One is ourselves, and we'll do that in a minute. The other is a phenomena called spurious wake up, which particularly happens on Windows systems. Sometimes it just happens. The condition variable will be erroneously woken up. But the way that I've structured the code here means, well, so what? If it does wake up erroneously, all that will happen is the process will go back round to the while loop, check the state of the empty flag, and continue, at which point it'll go back to sleep. Our queue object only has two methods that allow us to insert items into the queue, push back and push front, and therefore we can assume that when we use these functions that we have added an item to the queue. So this would make a good place to signal our condition variable to wake up. So I'll do it for push back and for push front. So now our tight loop is sat waiting. If we've called the wait function and there's nothing in the queue, it's waiting until an item has been written to the queue, and it will wait without consuming our CPU cores. The threads have been put to sleep. It will sleep until we add another item to the queue, at which point we notify our condition variable to wake up. This function stops blocking, our queue is no longer empty, and therefore our wait function returns control back to the original caller. So now I'm going to recompile our server application to make use of this new wait functionality. I want it to process as many packets as possible, so I'm specifying -1, but I do want it to wait. So now I'll run the server, it's running as before, and I can see that the net server application is currently consuming 0% of the CPU. But that means it could have just stopped working, right? So let's actually launch some client applications at the same time. So here I have two clients which are consuming full processing cores, but our server is doing nothing. So let's send a ping message. No, they still seem to be working, and we'll get the clients to communicate with each other. That seems to be working too. Whilst I've got these windows open, I think it's worth demonstrating the second problem I want to solve. At the moment, our server is running on port 60,000, and the server is programmed to simply accept and respond all and anything that connects to port 60,000. So we've seen that it quite happily accepts our client programs, which are doing what they should do and are well behaved, but it will also accept connections from other things too. So here is my test client. As you can see, I'm connecting to localhost on port 60,000, and I'll open it. The server has very happily approved this connection. Now I'll send some random data. And oh dear, we can see, well, the server's not crashed, but we've suddenly allocated 1.6 gigabytes of memory. That's pretty scary stuff. You can see the server's still behaving, but that memory ain't disappearing. We've got a problem here. Unsolicited connections can quite happily connect to our server and cause all sorts of chaos. This random junk has been interpreted in some way as a command or a message, and in some way the server has tried to deal with it. The thing is, as soon as we put our server anywhere in the real world, things are going to try and connect to it. You've got things like port sniffers, things just looking for open ports and servers to try and wreak havoc with. You've got accidental connections from quite legitimate bits of software not realizing that you've used a port that they're expected to use. You may also have another problem, and that's more common with the casual coding approach, is that you'll run an old version of your client with a new version of your server or vice versa, and things just won't quite behave as you expect them to. Either way, we need a process whereby the server can validate whether the client is something that it wants to interact with. The reason we just saw a problem with the consumption of memory is because the first thing our server expects to read in all circumstances is a message header, at which point it'll read the identity of the packet, which was garbage, and then it'll go on to read 4 bytes that represent the size of the body it is to read next. Of course, those 4 bytes that we sent were garbage also, but the system has no way of knowing that, and it is indeed primed to allocate a buffer large enough to read the body that it has been told to by this header. And quite a few viewers from the previous episode immediately recognised this as being a problem. How wise is it to let the client determine anything to do with the size of things on the server? And as with all these things, the answer is it depends. If you're in control of the situation, for example, you're talking to a robotic car on your own local network, and there's nothing going to interfere with it, you just want to have fun, then fine, nothing wrong with this at all. If, however, you're creating something which you know is going to be attacked, and in some way people are going to try and compromise your efforts, then yes, you probably do need to protect against it. My method of protection here is to just simply reject and automatically ban all clients that don't immediately connect to the server with something I expect them to send. A slightly more sophisticated approach would be to only send messages which conform to known structures in advance. And we'll actually see by the end of this series that this situation is actually highly applicable to what we're building. But whilst I'm developing it, I'm going to keep with our flexible sizing approach. In our system, both the server and the client applications implement a connection. And it is this connection which is our abstraction in this system to handle ASIO and the transfer of data around the network. In principle, the connection does the following. We somehow open it. And if that's a successful connection, we then go on to sit asynchronously in a function called readHeader. And when the connection receives some data, this readHeader method will interpret it as a header, and if necessary call a readBody function. Either way, it ultimately ends up just coming back to readHeader. And it will asynchronously respond to information coming in until the connection is closed. In the case of being a server, I'm going to insist that the client starts to communicate with me in a special way. To start with, I'm going to allow the connection to be opened, but I'm not going to go straight to readHeader. We're going to perform a handshake with the client first. In fact, I'm going to ask the client to solve a little puzzle for me. That way I can be certain it's a client I actually want to do business with. So I'm going to break into this little sequence with another function which is going to be write validation, which is going to send the puzzle to the client. We're going to expect a response from the client, so I'm going to sit in a function, asynchronously of course, called read validation. If the response from the client is what I expect it to be, then fine, the client has passed its little test, and I'll sit in readHeader again and carry on just as before. I've effectively put a hard wall in place on my server application. If anything violates these rules, I'm going to assume it's a bad client and just not do any business with it. I'm just going to close them down. I could keep track of this too and decide to add that client to a banned list if they have, say, more than 5 bad attempts at connecting. Interestingly, this means that things are slightly different now for a client. Once a connection is opened, the first thing a client must do is expect to be sent some data. This data contains the elements of the puzzle the server is asking it to solve. So it must solve that puzzle and then write it back to the server, after which it too can then go and sit in readHeader, waiting like a normal application. It will either be shut down by the server because it's failed the test, or it'll have passed the test and the server will start sending it valid and useful information. So depending upon whether our connection is configured to be owned by a server or owned by a client determines the order we need to asynchronously read and write validation data. I'm also going to assume that once a particular connection has been validated, it doesn't need to be revalidated at some point in the future, but you could implement your own protocol that way. For example, every 20 messages exchanged must have a revalidation message, and we'll have a look at how this validation works now. Let's consider what a useful validation is. In the most basic form, we could simply have the client send a message directly to the server. The first thing it sends is hello. And therefore the server knows that if a client that's just connected to it sends anything other than the first 5 bytes being hello, then that client is to be rejected. The problem with this approach is it's not going to take very long for somebody trying to break into your system to work out that the first thing a client does is send the message hello. So this approach is no good. A better approach is that upon connection, the server sends something to the client. Let's say the server says hello, to which the client is expected to respond with a known response. Well, this is better, but it wouldn't take somebody very long and with enough commitment to work out that for a particular response sent by the server, you respond with a known answer from the client. So we need something that's particularly tough to work out what's happening. I'm going to start with the server generating some random data, and then it does two things. Firstly, it sends that random data to the client, but at the same time also calculates a function of this random data. The client receives this random data, also performs a function of it, and sends the result back to the server. If the function of the data calculated by the client is equal to the function of the data calculated by the server, then from the server's perspective, there's a high degree of confidence that the client is something I actually want to do business with. Working with random data like this means that for anybody watching the network, they don't have a repetitive data source with which they can use to experiment to change bits and see what happens to the responses. The nature of the function implemented by the client and the server must be a closely guarded secret. For example, let's say my random data was A, C, D, E, B, and all my function did was add 1 to these values, then the client would respond with B, D, E, F, C. And trust me, it won't take many people very long to work out what's happened here. The complexity and nature of your function has been compromised, therefore somebody with enough motivation can build a fake version of your client and start communicating with your server. There's a whole world of research on creating good cryptographic functions like this. And I will state straight away, I'm not actually an expert in cybersecurity at all. This is not something I really know very much about. But I do know that if I want to make it difficult, then I want to make sure that my function that scrambles this random data does so in a way which is probably irretrievable, unless you know how the function did it in the first place. Here in the connection class, I'm going to add a function which will scramble the data. So the data I'm going to be sending are a uint64t. That's 8 bytes of data. And given 8 bytes of data, I'm going to XOR it with some constant, and I'm going to move its bits around internally, and then I'm going to XOR it with a different constant again. And, for example, one of these constants could have something like the version number. This way you can stop old clients talking to new servers. Now, I would just like to stress again, I am not a security expert at all. And I doubt that even this would present much of a challenge to somebody who is determined enough to compromise your system. You probably want something dynamic in there, such as the whole thing is rotated by whatever the 4th byte was modulated with a prime number. Something like that thrown in too. Regardless, it doesn't matter what's in your Scramble function, provided it does a good enough job of making sure that whoever's trying to unscramble it is going to have a tough time. And it goes without saying that any executables that I release related to this video series, this will not be the scrambling function. I'll also add to our connection class some variables to represent this handshake information. Handshake out is what the connection will be sending outwards. Handshake in is what the connection has received as a result or as data to scramble in the first place. And handshake check is used by the server to perform the comparison to see if the client is valid or not. So let's implement these. In the constructor of the connection, we know whether the connection is owned by a server or a client. And this was quite an important distinction to make, if for no other reason than to handle this validation process. So I wish to be sensitive to that. If the owner is a server, then I'm expected to generate some random data and then send that out to the connection. Now, when I say generate random data, all I really mean is make sure the data isn't the same each and every time, because that can be easily compromised. And so I just want some data that changes. An easy way of getting changing data is to look at the time. And in this case, I'm taking a system clock value, I'm turning it into a duration by comparing it with the epoch, and then just counting how many, well, whatever, it doesn't matter, I think it's milliseconds in this case, have elapsed since the epoch. That's going to be the data I send out. Since I've generated the data here, I'm also going to generate the scrambled version of the data, which is this server connection's private copy of it. It will compare what the client sends next with this information. If the owner of this connection was a client, then we don't need to do any of this generation of data. We just want to sit waiting for data to be sent from the server, which we can do here. The connector server function is only ever called by clients. So instead of going straight to the read header function, we're going to go to a new read validation function. Whilst we're here, the connector client function is only ever called by servers. Previously, that too would just go straight into reading the header. But instead now, I want the server to immediately write some validation data. Any new connection comes, immediately gets data thrown at it, and then the server will sit and wait asynchronously for that connection to respond with the correct result. These two functions have introduced two more functions, write and read validation. Well, write validation, by now we're all familiar with ASIO, this should be actually quite simple to understand. All it's going to do is write that handshake out variable. So we call the async write, we create an ASIO buffer that wraps up the handshake out variable, we pass in the size, we check for error codes. Once we've written the handshake out data, if we're a client, all we can do is then sit and wait for the server to respond with a header. If the server decided to close down this client connection, well, this would fail. We'd close the socket. Or the next waiting for read header asynchronously, that would fail, and so the connection would be closed. Either way, if the server doesn't like us, we're going to get shut down. Read validation is only slightly more complicated. You'll notice that for this function, I'm going to pass in a pointer to the server class. Ultimately, this is so I can hook into a server interface function to inform the user or the derived class that encapsulates the server that a client has been validated. That might be useful for game-related things. It's slightly different to a client being connected. Regardless, the first thing that's going to happen is we're going to asynchronously read 8 bytes of data into handshake in. If some error occurred, we're just going to terminate the connection. Now, this read validation function has a different behavior depending upon whether we're a server or a client in this instance. If we're a server, we're expecting read validation to read the data that has been computed by the client. If we are the client, we're expecting the validation data to be the random data provided by the server. So again, depending on the type of owner that we have, we're going to respond slightly differently. I'll start with being a client first, because it's a bit simpler. We've just received a bunch of random data from the server, so we're going to use our common scrambling function to transform that input data into something we're going to send back. So all we need to do next is actually send that result, which is handled by our write validation function. As you can see, it sent the handshake out variable. But in the event that we are a server, the data coming in through read validation will be the response from a client. So I want to check to make sure that that data that's just been sent in is what I expect it to be as a solution to the random data I sent out. If I get here, then the client has successfully solved the little puzzle that I've sent it, and then I'm going to call a function from the server pointer that we've sent through called onClientValidated, and it will send through the pointer that represents this particular client. This means the client passed. Therefore, for this connection, there's nothing left to do other than to sit reading the header. We've guarded access to these read header functions from the perspective of being both a client and a server. This guarding has been implemented through these read validation and write validation functions. A little task must be solved before we allow either the client or the server to start running its read header function. This gives us a degree of protection against connections that don't behave in a way we expect them to. Therefore, we can finish this off with, if the handshake wasn't what we expected it to be, we simply shut down the connection. We could track this in more detail and add them to a blacklist if necessary, but for now I'm just going to shut it down. We've thrown into the mix here this onClientValidated function, which is expected of a server interface object. So let's go and add that publicly to our server interface. We already have some functions here declared as virtual, which we would expect the user to override when they're deriving their own server implementation. And so I'm just going to add this one to the bottom as public. The primary difference between onClientConnect and onClientValidated is onClientConnect can be anything at all that connects to the system. As we saw earlier, I was connecting to our server using PuTTY. I might want to filter those connections at the IP level. And that's a great first pass. Perhaps you only want to allow things to connect to your server that have IP addresses that you know in advance. On client validated is called once this little puzzle has been solved. So there's a really good chance now that the client is actually going to behave in a way that we expect it to. Before we can test this, a couple of little housekeeping things. Our read validation function now needs this server pointer. So I'm going to modify this connect to client function definition to also include this pointer. Because this is just a pointer and we've not yet included it up here, the server hasn't been included, I'm just going to forward declare it. It's completely valid to do, a little bit spaghetti perhaps, but hey, solves the problem nicely. This connect to client function is called by the server implementation in the wait for client connection asynchronous function. We can see it here. We look through the deck of connections that we've got and we connect to it passing in a unique identifier for this client. Well, I also want to pass in the this pointer now. I've chosen to just rebuild the server side of the application only, not the client. So the client is now out of date. Let's launch the server. Server seems happy. Let's launch a client. Well, we can see that the connection has been allowed, but it was never validated. And we can see that the first thing that the client tried to do was send something to the server and it got disconnected. Let's just try that again. So these are old clients now, they're not doing the validation, but I pressed the 1 key which would normally ping the server and it failed. We can also try with putty. So we can see here that the server immediately sent some data, it's this junk at the top of the terminal, and if I respond with something, well, the server didn't like it and shut down the connection. I'm not going to close down this server, but I'm going to immediately build the client. The client and the server share the same connection code, so they now both have that same scrambling function. There's our server. Let's have a look at our new client. Server accepted connection straight away. Connection has been improved and the client has been validated. Let's just open up another client too. Ping, 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 ping. All is behaving as we'd expect it to. And the nice thing is we haven't had to actually change anything to do with our server or our client. This has been a change in the library which has completely encapsulated this validation exchange. And so there you have it. With that, the networking side of the code is pretty much finished. I'm sure there's going to be some slight tweaks to it as we start implementing the actual MMO game, but fundamentally I think I'm happy that it's going to be robust enough and sensible enough, simple enough and flexible enough for us to have some fun with in the next video. Until then, if you've enjoyed this video, a thumbs up please. I know it's been a quick one. Sorry about that. Sometimes real life just gets in the way. Have a think about subscribing, and I'll see you next time. Take care.